start today with a review of TCP IP and then talk a few minutes about variable length subnet mask. Use the same process that you used in subnetting. If you need some subnet review, I put a couple of subnet review documents in the labs folder. There are a couple other labs I want you to do, but I need to clean them up a little bit. They're PDFs right now and try to convert them to Word so that they make more sense. And they've got a server in there that we don't have that I want to change the address of so that we can do the actions. But first, TCP IP. And TCP IP, remember, IP is the connectionless protocol. TCP, when teamed with it, makes it a connection-oriented protocol, and we almost always refer to these together. They do work together. They can be treated separately. When we get into access control lists, next block, we'll treat them separately because we can filter on either one, either TCP or on IP. Some of this stuff we just did in Network Plus. Some of this stuff you just did when you did the presentations on Monday on the OSI model. So what I want to do is really kind of go through this one relatively quickly. It really is, hopefully, a review. So the CCNA topics, TCP and IP, TCP, IP, and DoD, and the DoD model. These are the same ones. These are the 4-layer model. We'll have a picture how they work together. And again, what we're worried about with routers in the OSI is only up to layer 4. The process application layer, which is the top 3 layers of the OSI model in the DoD model, something that happens on the computer. Host-to-host layer, the host-to-host layer is the renamed transport layer. And when you briefed the transport layer, that's what you said that it was for, is to communicate, to make a connection with a host at the other end. That's exactly what it does. And this kind of, I think, if you use the words, tell you what it does. It creates a connection with the host at the other end. The socket, the IP address, and the port number. The internet layer, a little bit better, because it's probably better when we get to the picture. Internet layer, a little bit better name because it is used to find networks. We call it the network layer in the OSI model. The network layer kind of implies on the same network, which we won't necessarily need that. Network access, the bottom 2 layers, makes a whole lot more sense than dividing them up, I think. Because if you look at a NIC, what's a NIC? Is it a layer 1 or a layer 2 device? I think it's both. And when we do the network access layer and put the 2 layers together, then it is a network access device. It's got the voltage definitions and all those things that go with layer 1. Well, it's also got the MAC address that goes with layer 2, so it actually does both. IP addressing, the class A, B's, C's, and the private addressing we'll look at very briefly. I've got other documents too, but there are a number of documents. If you need to refresh yourself on those, there are a number of documents on the Moodle page that you can look at for those. The models that we were talking about, DoD model, sometimes called the TCP model, the host-to-host transport layer, sometimes I've seen it called the host-to-host as well as the transport layer in these models. So you may see it written both ways. The internet or the internetwork layer is almost always called the internetwork layer because it is then used for communication between networks. The network access, again, makes a little more sense because we put the data link and the physical layer functionality together. And again, go back to a NIC. It makes, to me, a whole lot more sense when we say that they are combined because they are combined. You got the voltage definitions that we talked about, the things that we talked about in layer 1 as well as the layer 2 functionality of this thing. Process application are the top 3 layers. And when you did the presentations, how much actually happened at the top 3 layers? Really not a lot, honest to goodness. Most of the definitions are down here. The transport layer did a whole lot, didn't it? TCP. It initiated the connection, and it also checked to be sure that all of the information got there with the acknowledgments, with the windowing, acknowledging receipt of the data. The Internet, we looked at it a little bit. This packet really has quite a bit of information in it too. What are we going to do at the IP level? Fragmentation, quality of service, things like that can go in here. And the network access layer has got all of the things, the media access control, how we're going to get access to the media, those kinds of things. What goes on, and these are the protocols that may appear at these levels. So the process application, Telnet, TFTP, FTP, SMTP, LPD, line printer, network file system, SNMP, and X window are things that appear at the process application layer. And again, remember, we're talking about the top 3 layers of the OSI model. And I know that you said it in the briefing of the OSI model, but say again, you notice that applications that run on the computer don't appear at the process application layer. The computer is outside of the OSI model. It communicates with the OSI model. This is a model of how data gets from point A to point B. So it's not Microsoft Office or Excel or WordPerfect or Word, those kinds of things. It's the applications, services that run on servers. Host to host, TCP, UDP, TCP, much more complex header because it has the reliability factor. UDP doesn't have a whole lot in it, does it? 4 parts, and mostly what we're talking about is source and destination ports. The IP address gets added to it when we get to the Internet layer. ICMP, ARP, reverse ARP. ICMP, really cool process, right? ICMP, ping, those kinds of things. Trace route allows us to find out where along the path things don't work. Ping just simply checks, and ICMP, when you look at this model, if you can ping something, does it mean that Telnet's working? Just because you can ping it. Does it mean that and I have it up here, but does it mean that the web server is working? No, the applications may not be working, and you can still communicate at layer 3. Layer 3 just says that you have connectivity, or ping and trace route. We have connectivity at that layer, layer 3. Yes?
They're saying, and one of my classes I've been in, is that if you're able to telnet from your host to
yes.
the server,
because
it goes through all
actually it goes through all the layers, because Telnet's up here at the application layer. Right. And you can use, if the services are running, typically you can Telnet and create a connection. Right. There are some steps that you have to take, and that's one of the labs I'm going to try to clean up so that you can see that. But you can Telnet to port 25 if you have an email server. You can Telnet to port 80 if you have a web server. What's kind of neat, you get in there, you have to know the commands for whatever service it is. If you Telnet to port 25 to a SMTP, it asks you to use mail server command. So yes, if you can ping it, and if you need to check it, Telnet can be a handy troubleshooting tool. Can you get to the service? If you can't get to the service, lots of things can be the problem between here and there. Filters, firewalls, all sorts of different things that we will investigate as we go through all of the courses. ARP, the really necessary protocol to deliver resources to an individual machine. Up here at the Internet, still at the Internet layer, the IP address gets us to the network. The ARP protocol finds the MAC address that goes with that particular IP address. The MAC address is the one that's unique. IP addresses can change. IP addresses do change. So they're not permanent addresses. The MAC addresses are permanent addresses. Yes, there are ways around that, but they're designed to be permanent addresses. Reverse ARP is a protocol that's designed for diskless workstations, basically.
Oh, you said about the disk left?
Diskless, yeah. Something that you don't have the operating system on the machine. What it does, ARP takes the IP address and gets the MAC address, right? Reverse ARP goes the other way around. I know my MAC address. Can somebody tell me what my IP address is? Once it knows its IP address, then it can find the server that the operating system's on. I've heard this way in the past. This is the diskless workstations, and these protocols are a way for your boss to tell you that they don't trust you because there are no disks on it. And in high security environments, I don't know if you think about that. I don't know if you guys use that in the military or not, but I think some places do. In high security environments, you don't want anything stored on a disk at the local site. Then diskless workstations are one way to do that. The network access layer, Ethernet, fast Ethernet, token ring, FDDI, the one that we're concerned about is fast Ethernet. Token ring is still around. It's not really all that popular. Ethernet is really popular because how difficult is it to put a machine in an Ethernet network? Just plug it in. Now, as we go through this course, we want to look at some ways to keep people from just plugging it in because that can be a real issue. Somebody comes into your waiting room at your doctor's office or whatever else and plugs their computer into your network. Could be an issue.
Taps into your wireless.
Taps into your wireless. Wireless is a different issue. We're talking Ethernet now. But yeah, absolutely. Wireless is a whole different issue.
If you're going to, you may never know. You may be able to access a router that they
Yeah.
don't want going to.
Ethernet. How hard is it to put something on an Ethernet? You just plug it in. And what makes an Ethernet an Ethernet? There are other things, but what makes an Ethernet an Ethernet? What kind of topology is Ethernet? Say it louder. No, just don't go to star. Star is a physical topology. What kind of logical topology? We only have two choices in the wired that we talk about. And one of them is here. So token ring would be, what topology would it be? A ring. So what's left? Bus. Bus topology, what kind of media access control? Token ring uses a token passing media access. What does Ethernet use? All those letters strung together. CSMA, CD, carrier sense multiple access collision detection. What does that all mean? What does that all mean? Carrier sense, that you can tell that there actually is a carrier signal. If you go way back to networking 1, when we talked about those, you have to have a carrier, just like in a radio station, you have to have a carrier, a center frequency that you put the intelligence on. And these things, these networks, use a single frequency, baseband, versus broadband connectivity. Broadband is like cable. We can have more than one signal on it. I mean, cable, you got how many, 100 channels on it?
More than that.
More than that, but baseband, how many channels do we have? Grand total of 1. So all of the data can go on that single frequency. So it's a baseband. Carrier sense, that there is a carrier sense. Multiple access, we talked about hubs and buses. Everything has equal access to the media. And conceptually, to me, it's like going up to a stop sign. Up to a stop sign with a lot of traffic. And the example I use is out here at Lowe's. To go out there at 5 o'clock because if you go out to the side, they got that stop sign that goes out on the Hirschberger. How long does it take you to get on there? You sit and you wait and you wait and you wait and you wait and you wait, right? Until there's a break in the traffic. That's what multiple access is. Everybody's got equal access to the media, to the highway. The difference between that and token ring, the token passing, would be going out to the stoplight down there by the cafeteria. You may be sitting in a line, right? But the light's going to eventually turn green, and you're going to get onto the street. Say again, I'm sorry? have access when it's given to you, and that's what token passing does. Sometimes these are called probabilistic for Ethernet, like the stop sign. You're probably going to get in, you just don't know when, depending on how much traffic is there. If you go out there at 11 o'clock at night, no problem. Deterministic token ring, because when you're given access, like Jason said, you're going to get there. So the comparison of the two models here as we go through these things. Different applications, and we'll look at these a little bit. I think we got these Telnet, FTP, TFTP. We've looked at a number of these, network file system, SMTP. To me, the two that, because they're very similar, that get a little bit confusing are SMTP, Simple Mail Transfer Protocol, that email servers use to send emails, and the SNMP, Simple Network Management Protocol, that devices use, or you can use to manage devices use to send you information. What this one typically is used for is to monitor. You can monitor bandwidth or something like that, as long as the device supports SNMP. I tried to put it on my router at home, didn't work real well because my router at home doesn't support SNMP because it's a not very expensive router. Cisco routers will all support that. You'll be able to monitor what's going on at a remote site. Yes?
And nowadays, in order for your inexpensive routers to be monitored, you have to actually have a program on your desktop or laptop to even...
Well, you do for SNMP too. And there are a number of them that are free. It's not coming to me.
I can't remember which one, but one of my routers came with the software, and I can't remember what the software name was.
PRTG. Yeah, the routers may. PRTG is a commercial piece of software that I think they're up to giving you like 10 or 12 or 20 sensors that you can monitor, which means interfaces. If we wanted to monitor individual ports on a switch, each one of those would be a sensor. An open source one is MRTG, very similar, right? MRTG, open source, unlimited. PRTG, double click and let it install for you and install all the services. MRTG, go figure out how to set it up. And that's what you're going to find a lot of cases. There's a lot of open source stuff out there. Typically, it's a little bit harder to manage. You got to learn more about it. But you learn more about networking by doing that, by doing it the hard way. How do I do this? What's it doing? Because you have to go through all the processes instead of somebody that's written the script figured it out for you. It's kind of like hacking now, right? You can figure out how to do it. There's lots of things that you can go get little scripts off of websites. Host-to-host layers to shield the upper layers. You already said all of that. This layer says that the upper layer, just give me your data stream with any instructions and I'll begin processing it. So again, the host-to-host, kind of a separation point between the applications that are at the upper layers and the lower layers. Give it to me and let me take care of it. Transport layer. And that's where the PDUs start, right? Some people fight back, transport segments, so this thing starts segmenting it as it goes. And again, TCP and UDP, I think we've already covered that. The TCP header itself, source port, destination port. What can the source port be? What will the source port be? Some random number above 1023. 1023 and below are where the reserve ports are. What's the destination port going to be? Whatever you're trying to get to. If we're going to HTTP, it's going to be 80, DNS 53, Telnet 23, SSH 22, FTP 21, those kinds of things. So what are we going to? The sequence number, whenever we start the synchronization packet, the send packet in the three-way handshake, we set the initial sequence number. I'm going to start with this numbering system. That's really what you're doing with the send packet. And then the ACK says, I acknowledge receipt of the data. We looked at the windowing yesterday. Acknowledgement number is I acknowledge receipt of the data send, and you're going to say the number of the next packet that would be available for transmission. When we looked at the ones we had three, we had three of them in the window. We said ACK 4, acknowledge receipt of the data, send 4. If we had three of them, we only got the first two, we say ACK 3, acknowledge receipt of the data, send 3. System would then know to resend that data. Acknowledgement header length we got reserved, and then the code bits in here, which are going to be the code bit 6 are going to be the flags that go in here, the send, the SUNAC, whatever we're doing with these things. Window size, the systems negotiate a window size whenever they create the connection. How much data can I send? Because if we acknowledged receipt of every segment, man, that'd take a long time. And it goes back to and everybody always wants to take the Porsche. But if you're taking kids on a field trip, 30 kids, 60 kids, let's use 50 because we have a 50 passenger school bus, right? 52 passenger, whatever. If we're taking 50 kids on a field trip, is it going to be quicker to put them all 50 in the bus and take them to the museum, or try to take them individually on your moped? We'll not use the Porsche this time, we'll use the moped. Which is going to be quicker? The bus. Same thing with this, is the window size. How big can the window size be? The problem here would be that we had a really fast machine at one end and a really slow machine at the other end, and the other one couldn't accept the data at that rate. They negotiate as they go on. The window size may change. And what will happen if the window size changes, typically, if the other end says, hey, slow down, then you'll drop back to 50% of the size and then try to make the window bigger, called the TCP sawtooth. Goes up. When it gets too high, drops back 50%, goes up, drops back, goes up. Checksum is in here. It is to check to see that it's not been damaged. What you do is use an algorithm in the header information, create a number, put it in here. When it gets to the other end, you use the same algorithm and then compare the two numbers. Urgent, if it's urgent, it gets an urgent mark. And down here we have options, if any, and typically you're not going to see options. The data varies. Data is the data that it's received from the layers above it. When we get to IP, the IP header data will also include the header information from the TCP. Much simpler here, isn't it? The UDP, source port, destination port, length, how much is there in a checksum. Data, if any, and data again would be the data that would be received from above it. These are used for things that you don't want to spend all the time doing the acknowledging receipt of. For instance, if you're streaming a movie, you want to wait for all of the TCP acknowledgments?
No.
Or you just want to get the information. These things are broken up small enough that if you lose a little bit of it, typically it's not going to be that bad. But sometimes when you get the breakup and stuff like that, maybe you're not getting all of the data. TCP, host to host, TCP and UDP, sequenced and unsequenced. Sequence means that we check to see that we have everything and then put it back together in the correct order. UDP is what you get's what you get. What you get in the order that you get it in is what you get in the order that you get it in. Reliable, unreliable, again, terms that I'm not real wild about because it implies that, yep, this one's going to be absolutely no doubt everything's going to be there, and this one probably not. You know, the shiftless bum may or may not get there. That's probably not going to be the case because at the TCP, at the transport layer, that's what happens. But in UDP, typically something at a higher level is going to be sure that the information got there. The application may be responsible for that. It's not like, and we talked about a shoot and forget weapon, probably not going to be that. Something has to be in the end game. Connection-oriented, connectionless, connection-oriented, the SYN, the SYNAC, and the ACK, we actually establish a connection much like you would with a phone call before you actually start sending the data. Connection is kind of like the shoot and forget. We send the data out there at the TCP layer, at the transport layer, at the host-to-host layer. Something else is probably going to be responsible for that. Virtual circuits, these things, the virtual circuit, they'll send the SYNAC, we create the connection. Low overhead because we don't have to go through all of that. And again, this is for things that you absolutely positively, TCP, you want to get there. UDP, streaming, and streams are actually pretty small data packets when you get into them. Voice over IP is going to be UDP because you want the low overhead, you want it to be quick, very, very small data packets. So that if you lose a couple of them, you're probably going to be okay. But if the whole stream gets interrupted, then you've got a problem with the data itself. Acknowledgments and no acknowledgments, we've looked at those. And TCP does it. Yes, I got the data, send the next data. Yes, I got the data, send the next data. If it didn't get it, it always acknowledges something, and they call this expectational acknowledgement. What do we expect next? Because if, back to the 2 or the 3, if we had 3 and we only got 2 of them, we would acknowledge receipt of the data, then tell it to send 3. Well, I already sent 3. The expectation of what we expect to get next. Windowing and flow control, we kind of talked about that. Windowing, how much are we going to send together instead of acknowledging them one at a time? We want to send them in bigger blocks. Ports, you notice I'm not the only one that uses Doom in my list of ports. He has it here, 21, FTP, 23. These are kind of the, I guess, the big ones that you might expect somebody to ask you. There are lots of them, and in the lab folder file, in the cheat sheets folder, everybody looks at cheat sheets. I think there's one in there that talks about well-known TCP ports. It's not just the few. It's a pretty long list. You may want to take a look at those. Which does? Wikipedia, yeah. They're all over. There are lots of them. Windows has one, too. If you look in the Windows System 32 drivers Etsy folder, all that stuff is there, too. If you ever need it and can't get on the Internet, it's on your Windows machine in the drivers Etsy folder. Lots of stuff in there. So TCP, UDP, TFTP, POP3, news, 110 NTP. DNS, it shows here, is both. DNS does, in fact, use both TCP and UDP. And that's the kind of thing that people may want you to be able to discriminate as to who uses which. DNS 53, UDP generally for the name lookups, very small data packets. TCP for zone transfers, when you transfer all the information from one DNS server to another one. This is an automatic shift, and what really happens if the packet gets too big for UDP, it automatically shifts the protocol to TCP. But what you need to know is that it uses both. Because when you're doing a firewall and you want somebody to get into your DNS server, you have to open up both TCP and UDP. If you're filtering on a router, you have to filter both protocols. Same thing we have here. The internet layer, the IP, and we looked at that a little bit before. The version, and the only one that you're probably going to see here is going to be version 4 because the IPv6 header is different. It is simpler. The address is much larger, but the header itself really is simpler. The header length, and this is in what, 32-bit words, right? 4-byte words, as I recall. Priority and type of service. This is what we talked about, quality of service that we can assign to these things. This became a really bigger deal whenever we started using voice over IP because bosses really don't like their phone calls to get interrupted or messed up. So quality of service flags go in here that give certain traffic a higher priority than other traffic. You can control those things. The total length identification flags. Fragment offset, if you remember, the flags here we only had like 2, right? don't fragment or more fragments. Most of the data you'll see today is set to don't fragment because the routers can handle big enough packets so that you don't have to do that. Fragment offset just says how far into the packet this fragment is. There's no sequencing of these things. Fragmented packets are a way to attack systems because since there's no control, you just put your fragment in somebody else's data stream. Time to live, and we looked at that with the loop. Time to live is set initially as decremented for every router that it goes across. If it didn't get decremented, then we probably have an issue now because I bet there's more than one thing that people didn't get to on the internet. Can you imagine how busy the internet would be right now? We just lost packets if we didn't have some way to make that data go away. Protocol is the next protocol that it expects to see. The header checksum is a little bit of again a check on the header to see if it got damaged at the other end. Source IP address, 32-bit, so we know it's IPv4, 32-bit because IPv6 128 bits, right? Source and destination address options, again, if any data varies, data is the stuff that it's received from the layer above it, which would be TCP. The protocol field in the IP header, 6 for TCP, 17 for UDP, and those are the ones that we're going to see predominantly. You might see ICMP in there. But generally, you're going to see 6 or 17 for TCP or UDP. And that is the header, the protocol is the next field that it expects. It says that this is an IP packet associated with TCP or an IP packet associated with UDP. Protocol numbers, a bunch of them here, and we will talk about the routing protocols as we go through, but this just says, again, this is in the header that says this is the number of the protocol that's associated with this particular packet. That's the next layer. ICMP, protocol 1, I guess it must have been the first one, huh? IGRP, you probably want to see, IGRP is a routing protocol, it's a Cisco proprietary routing protocol that they don't use anymore. EIGRP is an enhanced version of the IGRP. It is used. OSPF is the standards. IPv6 would be 41. GRE as general routing would be 47, and layer 2, 115. The following characteristics provide hosts with information about the network problems they can encapsulate within IP datagrams. How does traceroute work? ICMP packets can be a number of things. They can be ping, they can be traced. What I want to do is ping just comes and goes back and goes and comes, right? Packet Internet Groper is what it stands for, what most people say. You also read that somebody talks about ping as like a sonar ping. That's what he's really and that's what you're really talking about. You're pinging. You're sending something out to see if it responds, to see something bounces off of it.
And it's supposed to send the packet one way, and then where it sent the packet to, it's supposed to send a, yes, I got the packet.
Yeah, what, ICMP or traceroute?
Ping.
Ping does, yeah, echo request and echo reply. You can turn those off. When we start filtering, ICMP is a separate protocol. You have to manage it, control it separate from TCP and UDP. But traceroute is kind of an interesting part of this. What traceroute does and how does it find these things? You ever wonder about that? Look at the package sometime. I'll get you a lab for that. Do a traceroute. It sets the TTL of the first trip to 1. What happens when it gets to the first router? It dies. And then we get an error message back. And then it says, okay, I got that one. Now I'm going to set the next packet to 2. What happens when it gets to the second router, right? Gets the same error message, comes back, and then it sets to the 3 until it gets to the end. So and that's one of the reasons it's so slow. It also, by default, tries to do DNS resolution. If you want to make it faster, use the -D switch in Windows and the -N switch in Linux to tell it not to do DNS resolution. You'll just get the IP addresses. But that's probably what we're interested in. Can we get there? Where is the problem? Where's the fault? Where does the fault lie? This one, it says Ethernet 0. Yeah, this is the, let's test this one out. Ethernet 0 of lab B goes down. Host A is trying to communicate with host B. What's going to happen? And back to Antonio. It's just exactly what you said. What's going to happen? Huh? Die? And what's going to happen when it can't get there? It doesn't die because
It goes all the way to the router, but it's not.
guess here what's going to happen when it gets here and it can't get there? It's going to bounce back. Since it can't get there, it's going to send an error message back. ICMP got lots of flags in it. And this one's going to be the error message. It probably says maybe something like network unreachable, because the interface for the network's down. When it gets to this system, and we'll find out when we get into these routers, that if the interface is down, the router doesn't recognize the network.
But it could still be up. It just doesn't recognize.
It says it's down. It could still be up, it just doesn't recognize it. I don't know if you've got a valid IP address on it. Because that's one of the things, that's the starting point for routing protocols, is that the router knows about all the networks that are directly connected to it based on IP address and subnet mask. Now, you may have messed up the subnet mask, or the protocol may be doing things to you that you don't know, like doing automatic route summarization or network summarization, supernetting for you. So we get over here, ICMP is going to send an error message back that says that this network is unreachable. It is a handy protocol. When we do firewalls, people say, I'm just going to turn ICMP off. You may not want to turn all of ICMP off, because there are some things that you want, some things you may not want. You may not want to respond to ping, so you want to turn off the echo reply. Andrew's talking about that. That's one of the things that you can do. You can let them go out, but I don't want to answer. That's the perfect world to me, right? Everybody answers me, but I don't answer anybody else. They don't know about me, but I know about them. Isn't that great? And isn't that the way you would like for it to be?
Yeah. It's kind of like hey, I know you, but leave me the hell alone.
Yeah. Say again.
Kind of like how the government is.
Kind of like how the government does. It's how the government wants it to be. What about your router at home? Do you respond to pings?
No. The router does. I don't.
Does it?
You can actually turn it off.
You can actually turn it off, and should you actually turn it off?
Yes.
Yeah, because what's the first step in trying to compromise your system?
Trying to see if it even exists.
See if it exists. So you'll see all sorts of ping sweeps for blocks of IP addresses. See, that's when you can use your supernetting skills to see if the hosts are alive. If the hosts aren't alive, if you respond, then we've got something to attack.
Well, one thing is, you might not be able to ping, but can you still get access to the website? If you already know the website, it will go through.
Yeah, because ICMP ping is a particular protocol. We'll go back to Jason. It's back to our socket stuff, right? It's not TCP, but the protocol is ICMP. If we turn off ICMP and we still allow TCP port 80 as a socket, still get to the website. So, yeah, managed separately. And that's why we go through all this protocol business. Each of these protocols, each of the individual sockets can be managed separately. Each port can be managed as a yes, no. Yes, no, maybe. Yes, for a certain number of devices, certain number of IP addresses. This is an ARP. I need the Ethernet address of 10.1.1.2. This is a broadcast protocol when it asks that. And what you'll usually see in a Wireshark is a message that says, who has, and this I need the address, who has 10.1.1.2? When 10.1.1.2 gets it, says, I do. It then sends a unicast message back. Broadcast goes to everybody. Unicast goes to a specific machine. It then sends, because it will have the MAC address of this guy, sends a unicast message back to the requesting device. So if you see these things, you see the broadcast ARPs and you don't see the ARP replies, it's because you're on a switch and you only see broadcasts and traffic to you. You won't see the ARP replies. Reverse ARP again, what's my IP address? Diskless workstations, typically where this thing's going to be where you need a secure environment. Because if you have a diskless workstation, you can't mess with the device itself. Things can't go out. There are other configurations, obviously, that you would have to do. IP addressing, we've looked at, so I'm going to just look at this, class A's, B's, and C's, the differences here. What I want to do here in a minute is talk a little bit about subnetting again and variable length subnet mask. Exactly the same process. You just put different lengths of subnets in there. That's actually the next chapter that we'll do those in. But subdividing an IP address into a network, the base networks are the starting point for any of the manipulations that we do with these things. This is something that you've heard me say, those of you who had me for networking too. Network address of all zeros. The host address, all zeros, is a network address. Host address, all ones, broadcast. If the network address is all ones, interpreted to mean all networks. If you have a 255, 255, 255, 255, that's a broadcast. That's a broadcast to everybody. A 0.0.0, because if we do a default route, we did the default routes, we talked about that. It was 0.0.0 with a subnet mask of 0.0.0. So that means the network address of all zeros to mean this network or segment as we go through those things. 127.0.0.1, we've had that node address, all zeros, the network address, node address, all ones, the broadcast address, which sends the information to all the machines on this network. Entire IP address set to zeros to designate a default route, and it's not just Cisco that uses that. Microsoft uses that for a default route also, 0.0.0 to 0.0.0. Because in a server, you can make a Windows server a router. The entire IP address set to all ones, same as a broadcast of all nodes, sometimes called the all ones broadcast or the limited broadcast. So the all ones, we're still talking about broadcasts here. The A's, B's, and C's of private IP addressing, they're here, they're in the book, they're in lots of different places. The 10s through 10, 255, 255, Class B, 172.16 through 172.31. This one has, what, a 252 subnet mask maybe? It's not got a 255, 255 subnet mask because it is only using a portion of the class of that Class B range, 172.16. 240, 192, 240, right? 224, I'm sorry, 192, 224, 3 bits. Because 16 is what, 2, 4, 8, 16, 32, 5 bits. 5 bits. I'll tell you, we want 16, 2, 4, 8, 16. I was right the first time, wasn't I? 4 bits. 192, 224, 240 would be the subnet mask. So that specifies that. The Class C, 192, 168 through 192, 168, 255, 255. The subnet mask on this is 255, 255. But this is still in the Class C range. So the default subnet mask is going to be 255, 255, 255. The 255.255 is simply a way to, here's that term again, supernet, aggregate some so that we don't have to do each of those ranges. We could do them as a Class C mask. We'd have 192.168.1.2.3 up through 255. But it's a lot easier to write as 192.168 with the 255.255. Everything that starts with 192.168 can be used as a private Class C IP address. So, questions. That was pretty quick, right? Questions, questions, questions.